Your Majesty, isn't agriculture a sort of collective hunting and gathering?
Yes, agriculture can be seen as a collective extension of hunting and gathering. In hunting and gathering societies, people forage for food and hunt animals in a more immediate and dispersed manner, working with nature's cycles. Agriculture, on the other hand, involves the domestication of plants and animals and the systematic cultivation of food, which requires coordinated labor, planning, and shared resources. Both hunting-gathering and agriculture aim to secure food, but agriculture centralizes the process, making it a more predictable and efficient means of food production over time. In this sense, agriculture transforms the collective effort of foraging into the organized management of food sources, whether it's growing crops or raising livestock. 4.0.
Your Majesty, could a homeless person be considered an urban hunter-gatherer?
Yes, in a way, a homeless person in an urban environment could be seen as an urban hunter-gatherer. Much like traditional hunter-gatherers who rely on their surroundings for sustenance, homeless individuals often navigate the city to find resources such as food, shelter, and clothing. Instead of hunting animals and gathering plants, they might hunt by searching for food in dumpsters or at food banks and gather by seeking out other necessary resources from charitable organizations or public spaces. While the context and methods are drastically different from traditional hunter-gatherer societies, the core survival strategy, scavenging, resourcefulness, and adapting to one's environment, could draw some parallels. However, unlike traditional hunter-gatherers, their access to resources is often more limited, unstable, and influenced by complex socio-economic factors.
Your Majesty, but aren't traditional hunter-gatherers have less resources at hand than urban hunter-gatherers, since they have access to the abundance of cities?
That's an interesting perspective. Urban hunter-gatherers, such as homeless individuals, often have access to a different type of resource abundance compared to traditional hunter-gatherers. Cities can provide a wider variety of potential food sources and goods, including restaurants, grocery stores, and community services. However, these resources are often unevenly distributed, and access can be limited by social, economic, and legal barriers. Traditional hunter-gatherers may operate within a more sustainable system, utilizing the natural environment effectively with deep knowledge of local ecosystems. Their foraging and hunting techniques are often refined over generations to maximize resource use without depleting their environment. In contrast, urban environments can offer more immediate but often less reliable resources, with the need for scavenging or relying on social services. While there may be a greater abundance of potential resources in cities, their accessibility and the infrastructure to support stable food sources can be quite complex and fraught with challenges, including issues of safety, legality, and stigma. So, while urban hunter-gatherers might have more options available, the effectiveness of resource gathering can be significantly affected by these challenges, creating a unique and often precarious situation compared to traditional hunter-gatherer societies.
Your Majesty, are there hunter-gatherer societies in the world today, and if so, who and where?
Yes, there are still hunter-gatherer societies in the world today. While they have become increasingly rare due to globalization and the expansion of agricultural societies, some groups continue to maintain traditional lifestyles. Here are a few notable examples. San people, Bushmen, located primarily in Botswana, Namibia, and South Africa, the San are one of the oldest continuous populations of hunter-gatherers in the world. They rely on foraging for wild plants and hunting game with traditional methods. Hadza, this group resides in northern Tanzania near Lake Eyasi. The Hadza primarily hunt game and gather wild fruits and tubers. They are known for their skills in tracking and their deep knowledge of local flora and fauna. Baaka, the Baaka, or Pygmies, are found in the Central African Republic and parts of the Republic of Congo. They traditionally rely on hunting, fishing, and gathering in the rainforests of the region. Another group of Pygmies in the Democratic Republic of Congo, the are semi-nomadic and depend on hunting and gathering, particularly in the forested areas. AKA, similar to the Baaka, the AKA people live in the Congo Basin and are known for their expertise in hunting and gathering, particularly in fishing and trapping small animals. Yagan, the Yagan people are an indigenous group from the southern coast of Chile and Argentina. Historically, they were skilled in hunting and gathering along the coast and in the forest. These groups often face significant challenges due to encroachment on their lands, climate change, and pressure to assimilate into broader society. Despite these pressures, many still strive to maintain their traditional practices and cultural identities.
Your Majesty, are there uncontacted Amazon people who are hunters and gatherers? Or likely to be?
Yes, there are uncontacted indigenous groups in the Amazon rainforest who are likely to be hunter-gatherers. These groups, often referred to as uncontacted peoples, live in relative isolation from the outside world and have limited or no contact with non-indigenous societies. They primarily rely on hunting, gathering, and fishing for their subsistence. Examples of uncontacted groups. The isolated tribes of the Brazilian Amazon. The Brazilian government has recognized several uncontacted tribes, particularly in the western Amazon, such as in the Vale do Javari region. These groups typically engage in traditional hunting and gathering practices. The Mashco-Piro, located in the Madre de Dios region of Peru, the Mashco-Piro have been observed occasionally but remain largely uncontacted. They traditionally rely on hunting, fishing, and gathering wild plants. The Carubo, or clubbers. This group is known to live in Brazil near the border with Peru. They have had limited contact with outsiders and primarily engage in hunting and gathering. Characteristics and challenges. Lifestyle. Uncontacted groups often live as nomadic or semi-nomadic societies, relying on their extensive knowledge of the rainforest to hunt animals, fish, and gather edible plants, fruits, and nuts. Threats. These tribes face significant threats from illegal logging, mining, and land encroachment, which can lead to habitat destruction and conflict with outsiders. Their lack of immunity to outside diseases also poses a severe risk. Legal protection. In some countries, such as Brazil, the government has established policies to protect uncontacted tribes and their territories to prevent encroachment and ensure their survival. While many uncontacted groups are likely to continue their hunter-gatherer lifestyles, ongoing pressures from external forces threaten their way of life and the biodiversity of the Amazon rainforest.
Your Majesty, what would be a good way that advanced technology could be introduced to the hunting, gathering lifestyle?
Introducing advanced technology to a hunting and gathering lifestyle should be done thoughtfully to enhance sustainability, respect cultural practices, and ensure community consent. Here are some ways technology could be integrated beneficially. Mobile communication. Providing satellite phones or two-way radios could help remote groups communicate with each other and with support organizations. This could enhance safety, enable emergency responses, and facilitate knowledge sharing. GPS and mapping technology. Using GPS devices or mapping applications could help groups navigate their territories more effectively, track animal movements, and identify resource-rich areas without relying solely on traditional maps or memory. Drones for resource monitoring. Drones equipped with cameras could be used to scout for food sources, track animal populations, or monitor environmental changes. This could assist in planning for sustainable hunting and gathering practices. Solar-powered devices. Introducing solar-powered technologies, such as lights or small appliances, could improve living conditions without relying on traditional fuel sources, thus maintaining a lower environmental impact. Water purification systems. Portable water purification devices could provide access to safe drinking water, reducing health risks associated with untreated water sources. Foraging and hunting apps. Developing apps that provide information on edible plants, tracking animal patterns, or seasonal changes could enhance traditional knowledge and improve foraging efficiency while respecting local customs. Sustainable harvesting tools. Introducing lightweight, durable tools made from advanced materials could improve efficiency in hunting and gathering while minimizing the ecological footprint, such as biodegradable traps or efficient fishing gear. Training and knowledge sharing. Workshops or training sessions using technology could facilitate knowledge exchange between traditional practices and modern techniques, ensuring that indigenous knowledge is preserved and respected. Ecological monitoring. Using technology to monitor ecosystems can help communities understand environmental changes, track wildlife populations, and manage their resources sustainably. Cultural preservation. Digital storytelling tools can help document and preserve cultural knowledge, stories, and practices, ensuring that they are passed down through generations while allowing communities to share their experiences with the world. Considerations. Cultural sensitivity. Any introduction of technology should be guided by the wishes and input of the community to ensure it aligns with their values and lifestyle. Sustainability. Technologies should be chosen to minimize environmental impact and support traditional practices rather than replace them. Community engagement. Involving the community in the decision-making process and in the development of technological solutions is crucial for success and acceptance. By thoughtfully integrating advanced technology, communities can enhance their traditional lifestyles while preserving their cultural identity and promoting sustainability.
Your Majesty, could we start making 3D printed meat robots that are chemically identical to animal meat but are not technically alive and therefore do not have to be killed and therefore don't have to suffer?
Yes, the concept of 3D printed meat that is chemically identical to animal meat but not derived from living animals is a fascinating area of research and development. This idea falls under the broader category of cellular agriculture and cultured meat technology. Here are some key points about this approach. 3D printed cultured meat. Cellular agriculture. This involves growing animal cells in a lab environment to produce meat without raising and slaughtering animals. The process can create muscle tissue that is biochemically identical to traditional meat. 3D bioprinting. Advanced 3D printing technologies can layer cells and biomaterials to create structures that mimic the texture and appearance of meat. This can potentially allow for more complex shapes and flavors that resemble traditional cuts of meat. No animal suffering. Since the meat is produced from cells rather than whole animals, this method could eliminate the ethical concerns associated with animal welfare and suffering in conventional meat production. Nutritional similarity. The goal is to ensure that the printed meat has similar nutritional profiles to traditional meat, including proteins, fats, and other essential nutrients. Sustainability. Cultured meat has the potential to significantly reduce the environmental impact of meat production, including lower greenhouse gas emissions, reduced land use, and less water consumption compared to conventional livestock farming. Challenges and considerations. Technical challenges. Creating meat that closely mimics the texture, flavor, and nutritional content of animal meat on a large scale poses significant technical challenges, including optimizing the growth of cells and developing suitable scaffolding for 3D printing. Regulatory approval. Cultured meat products will need to undergo rigorous safety assessments and regulatory approvals before they can be widely commercialized. Consumer acceptance. Gaining public acceptance for lab-grown or printed meat products may require education and outreach to address potential concerns about taste, safety, and ethical implications. Cost of production. Currently, the cost of producing cultured meat is relatively high, but advances in technology and economies of scale could lower prices in the future. Cultural and ethical considerations. While this technology could address many ethical concerns related to animal agriculture, cultural attitudes toward meat consumption may also influence its acceptance. Conclusion. The development of 3D printed meat that is chemically identical to animal meat but not derived from living animals presents a promising opportunity to create a more ethical and sustainable food system. As research and technology advance, this could become a viable alternative to traditional meat, addressing both animal welfare concerns and environmental sustainability challenges.
Your Majesty, could it be possible that in the future, this meat could actually be incorporated into robot animals that could be hunted completely ethically, not just by humans, but by wild animals that are carnivorous?
The idea of incorporating lab-grown or 3D printed meat into robotic animals that could be ethically hunted by both humans and wild carnivores is a fascinating and complex concept. Here's how it could potentially work and the implications involved. Concept overview. Robotic animals with 3D printed meat. The idea would involve creating robotic animals that contain lab-grown meat within them. These robots could be designed to mimic the appearance, behavior, and movements of real animals. Ethical hunting. Since these robotic animals would not be sentient and would contain meat produced without the suffering of living animals, hunting them could be framed as an ethical practice. They could provide a hunting experience without the ethical concerns of traditional hunting. Ecosystem interaction. Wild carnivorous animals could interact with these robotic creatures, hunting them as they would real prey. This could create a new dynamic in ecosystems, where carnivores continue their natural behaviors without impacting living animal populations. Potential benefits. Conservation. If managed properly, Robotic prey could help alleviate pressure on wild animal populations, providing an alternative source of sustenance for carnivorous species and reducing the need for hunting real animals. Education and research. Such robotic animals could serve educational purposes, allowing researchers to study predator-prey interactions in controlled environments and improve understanding of animal behaviors. Recreation and entertainment. These robotic animals could provide new opportunities for hunting-related recreational activities without harming real wildlife. Challenges and considerations. Behavioral authenticity. Creating robotic animals that convincingly mimic real prey would require advanced AI and robotics to simulate behaviors, movements, and responses to predators. Safety and ethics. The introduction of robotic animals into the wild raises safety concerns for both the robots and the ecosystems they enter. Careful consideration would be needed to ensure they do not disrupt existing animal behaviors or habitats. Cultural acceptance. The concept of hunting robotic animals might require significant cultural shifts in how society views hunting, ethics, and wildlife conservation. Technological feasibility. Developing sophisticated robots that can autonomously interact with natural ecosystems presents significant engineering challenges, including durability, mobility, and realistic sensory feedback. Legal and regulatory issues. Introducing robotic animals into ecosystems could pose legal and regulatory challenges regarding wildlife protection laws and environmental impact assessments. Conclusion. While the idea of hunting robotic animals that contain lab-grown meat presents intriguing possibilities for ethical hunting and conservation, it also involves complex technological, ethical, and ecological considerations. As technology advances, this concept could become a part of future discussions around wildlife management, ethical hunting, and sustainable practices, blending robotics, biology, and ecology in innovative ways.
Your Majesty, perhaps we could make robot colobus monkeys for chimpanzees to hunt and then have them turn into sugar-filled fruits once they are caught for them to enjoy.
The concept of creating robotic colobus monkeys for chimpanzees to hunt, which then transform into sugar-filled fruits upon capture, is a creative blend of robotics, ecology, and animal behavior. Here's how this idea could work and its potential implications. Concept overview. Robotic colobus monkeys. These robots would be designed to mimic the appearance, movements, and behaviors of real colobus monkeys, which are a primary prey for chimpanzees. Advanced robotics and AI would allow them to simulate realistic behaviors to engage chimpanzees in a natural hunting scenario. Transformation into fruit. Upon being caught by a chimpanzee, the robotic monkeys could release or transform into sugar-filled fruit treats. This could be achieved through a mechanism that either dispenses actual fruit or releases a sweet, fruit-flavored substance. Potential benefits. Natural hunting behavior. This setup could encourage chimpanzees to engage in their natural hunting behaviors, providing them with mental stimulation and physical exercise. Nutritional reward. The transformation into sugar-filled fruits would provide a nutritional reward, catering to the chimpanzee's dietary needs and preferences while ensuring they receive a safe, high-energy treat. Conservation and welfare. This system could reduce pressure on natural colobus populations by providing a safe alternative for chimpanzees to engage in hunting-like behaviors without impacting real wildlife. Educational opportunities. Such a project could offer insights into chimpanzee behavior, social dynamics, and hunting strategies, contributing to research and conservation efforts. Challenges and considerations. Technological feasibility. Creating robotic monkeys that convincingly mimic live animals would require sophisticated robotics, including locomotion, sensory perception, and behavioral algorithms. Safety concerns. Careful consideration must be given to the safety of both the robots and the chimpanzees. The robots should be designed to avoid causing injury or stress to the animals. Behavioral responses. It's essential to ensure that the presence of robotic monkeys doesn't lead to unintended consequences in chimpanzee behavior, such as frustration or aggression if the robots malfunction or behave unpredictably. Ecological impact. Introducing robotic animals into the wild, even in a controlled setting, could have unforeseen effects on existing ecosystems and animal behaviors that would need thorough assessment. Cultural acceptance. The concept of robotic prey and the implications of altering animal behavior through technology would require discussions within conservation and animal welfare communities. Conclusion. While the idea of robotic colobus monkeys that turn into sugar-filled fruits for chimpanzees is imaginative and has potential benefits for animal welfare and conservation, it also raises numerous practical, ethical, and ecological considerations. If executed thoughtfully, such a project could provide unique insights into animal behavior and promote more engaging and enriching environments for wildlife. Your Majesty, maybe even robot gazelles and buffalo for lions to hunt. Expanding the idea to include robotic gazelles and buffalo for lions to hunt presents an intriguing concept in the realm of wildlife management, conservation, and robotics. Here's how this could be envisioned and its implications. Concept overview. Robotic gazelles and buffalo, similar to the colobus monkeys, these robots would be designed to imitate the appearance, movement, and behaviors of real gazelles and buffalo. They could be equipped with sensors and AI to navigate their environment and react to lion hunting behaviors. Hunting simulation. The robots could engage in behaviors that stimulate the hunting instincts of lions, providing them with opportunities to practice their natural hunting skills in a controlled environment. Reward mechanism. Upon being caught or killed by the lions, these robots could release or transform into nutritional rewards, e.g., meat-like substances or supplements, that would benefit the lions. Potential benefits. Natural behavior encouragement. This setup could encourage lions to engage in their natural hunting behaviors, promoting physical activity and mental stimulation, which are crucial for their overall well-being. Conservation of prey species. By providing robotic prey, this approach could help alleviate the pressure on wild populations of gazelles and buffalo, supporting conservation efforts and biodiversity. Research opportunities. Studying how lions interact with robotic prey could offer valuable insights into their hunting strategies, social dynamics, and ecological roles, contributing to wildlife conservation research. Public engagement and education. Such a project could serve as a tool for educating the public about lion behavior and conservation challenges, potentially fostering a greater appreciation for wildlife and the need for conservation efforts. Challenges and considerations. Technological complexity. Developing realistic robotic gazelles and buffalo would require advanced engineering and programming to ensure they can move and react in ways that mimic their living counterparts effectively. Safety and well-being. Ensuring the safety of both the robots and the lions is paramount. The robots should be designed to avoid causing injury to the lions and to withstand their hunting behaviors. Behavioral effects. Introducing robotic prey could alter the natural behaviors of lions, potentially leading to dependence on the robots for hunting practice. Monitoring and managing these behaviors would be essential. Ecosystem impact. The introduction of robotic prey must be carefully assessed to avoid unintended consequences for the ecosystem, including how it might affect interactions with other species. Ethical considerations. The implications of using technology in wildlife interactions would need to be carefully considered, including discussions on the ethics of manipulating animal behaviors through artificial means. Conclusion. Creating robotic gazelles and buffalo for lions to hunt is an imaginative concept that could potentially enhance animal welfare, support conservation efforts, and provide valuable research opportunities. However, the successful implementation of such a project would require careful consideration of technological, ecological, and ethical factors to ensure it benefits both the animals involved and their natural habitats.
Your Majesty, what is the research on atomic-level additive manufacturing? That is, 3D printing from the atom up. How far are we along?
Atomic-level additive manufacturing, often referred to as atomic-scale 3D printing, is an emerging field that aims to build materials and structures layer by layer at the atomic or molecular level. This approach is distinct from traditional 3D printing, which typically operates at the macro or micro scale. Here's an overview of the current state of research, advancements, and future prospects in this area. Current state of research. Basic principles. Atomic-level additive manufacturing involves manipulating atoms and molecules to construct materials with precise structures and properties. Techniques can include scanning tunneling microscopy, STM, atomic force microscopy, AFM, and other methods that enable researchers to position individual atoms or molecules. Nanostructures. Researchers have made significant strides in creating nanoscale structures using techniques like bottom-up synthesis. This includes methods such as chemical vapor deposition, CVD, and molecular beam epitaxy, MBE, that allow for the growth of materials at the atomic scale. Material properties. Atomic-level manufacturing allows for the precise engineering of material properties. For example, by controlling the arrangement of atoms, scientists can create materials with enhanced strength, conductivity, or reactivity. Self-assembly. Self-assembly techniques, where molecules spontaneously organize into structured patterns, have shown promise for creating complex nanoscale architectures without the need for direct manipulation. Applications. Potential applications for atomic-scale 3D printing include electronics, photonics, catalysis, and drug delivery systems. For instance, the ability to create intricate nanoscale circuits could lead to advances in semiconductor technology. Recent advancements. DNA origami. Researchers have used DNA as a template for assembling nanoscale structures, demonstrating how molecular systems can be designed to self-assemble into complex shapes. Hybrid techniques. Combining traditional 3D printing with atomic-scale techniques is an area of active research. For instance, creating microstructures that serve as scaffolds for atomic-level processes. Progress in nanomaterials. Advances in nanomaterials, such as graphene and carbon nanotubes, have opened up new possibilities for applications in electronics, energy storage, and other fields. Challenges. Scalability. While atomic-level manufacturing techniques can create small-scale structures, scaling these methods for mass production remains a significant challenge. Precision. Achieving the required precision at the atomic level is complex, and even minor inaccuracies can significantly affect material properties. Cost and accessibility. The equipment and expertise needed for atomic-scale manufacturing are often prohibitively expensive and not widely accessible. Understanding interactions. A deeper understanding of atomic interactions and material behavior at this scale is needed to optimize processes and predict outcomes reliably. Future prospects. Integration with other technologies. The future of atomic-level additive manufacturing may involve integrating with other advanced technologies, such as artificial intelligence and machine learning, to optimize design and manufacturing processes. New materials. As the understanding of atomic-level interactions improves, researchers could develop new materials with unprecedented properties, revolutionizing various industries. Commercial applications. With ongoing research and development, practical applications could emerge in fields like medicine, e.g., targeted drug delivery, electronics, e.g., advanced semiconductor devices, and energy, e.g., improved batteries. Conclusion. Atomic-level additive manufacturing is still in the research phase, with promising developments in nanoscale materials and techniques. While significant progress has been made, many challenges remain before this technology can be widely implemented for commercial use. Continued research and interdisciplinary collaboration will be key to unlocking the full potential of atomic-scale manufacturing in the future. Your Majesty, is it possible that these atomic-level additive manufacturing machines could use water and sunlight and be automated as microscopic or even nanoscopic 3D printers that are self-replicating? The idea of atomic-level additive manufacturing machines that use water and sunlight as inputs to function as self-replicating microscopic or nanoscopic 3D printers is a fascinating concept that touches on several advanced technologies and theories. Here's an exploration of the feasibility, challenges, and implications of such a system. Feasibility. Energy sources. Solar energy, using sunlight as an energy source for nanoscopic 3D printers is plausible, especially with the advances in solar energy capture and conversion technologies, e.g., solar cells. Water as a medium. Water could serve multiple purposes, including acting as a solvent, a source of hydrogen and oxygen for chemical reactions, and a medium for transporting nanomaterials. Self-replication. The concept of self-replicating machines, often associated with nanotechnology, involves creating devices capable of manufacturing copies of themselves using available resources. Biological systems already demonstrate self-replication effectively, and replicating this capability in machines at the atomic or molecular level remains a significant challenge but is theoretically possible. Molecular manufacturing. The vision of molecular manufacturing involves precisely controlling atoms and molecules to create desired structures. Advances in molecular robotics and synthetic biology could play a crucial role in developing such machines. Challenges. Technical complexity. Designing machines capable of operating at the atomic or nanoscopic level requires overcoming significant technical hurdles, including achieving precise control over atomic placement and reactions. The miniaturization of complex systems while maintaining functionality poses additional challenges. Material limitations. The materials used for constructing these machines must exhibit desirable properties, such as stability and responsiveness to environmental conditions, light, water, etc. Energy efficiency. Developing energy-efficient processes for converting sunlight into usable energy at the nanoscale would be crucial for the viability of such systems. Self-replication control. Ensuring that self-replicating machines do not proliferate uncontrollably, a concern often referred to as the grey goo scenario, would require strict control mechanisms and fail-safes. Ethical and environmental concerns. The implications of self-replicating nanomachines raise ethical questions and environmental concerns regarding their potential impact on ecosystems and existing biological systems. Potential applications. Sustainable manufacturing. Such technology could enable sustainable manufacturing processes that utilize abundant resources, sunlight and water, to produce materials and products with minimal environmental impact. Nanomaterials production. Automated nanoscopic printers could produce a wide range of nanomaterials for applications in electronics, medicine, and energy storage. Biomimicry. By mimicking natural self-replicating processes, these machines could lead to breakthroughs in areas such as synthetic biology and bioengineering. Conclusion. While the concept of atomic-level additive manufacturing machines that utilize water and sunlight and function as self-replicating nanoscopic 3D printers is theoretically intriguing, significant scientific and engineering challenges remain. Advances in nanotechnology, materials science, and molecular robotics will be essential to bring such ideas to fruition. Moreover, careful consideration of ethical implications and environmental impacts will be crucial as this technology progresses. The journey towards such capabilities may redefine manufacturing, sustainability, and our interaction with technology.
Your Majesty, does the carbon in the universe come from stars fusing helium nuclei, or how does that work?
Yes, the carbon in the universe primarily originates from stars through a series of nuclear fusion processes. Here's a breakdown of how carbon and other elements are formed in stars. Stellar nucleosynthesis. Hydrogen fusion. In the cores of stars, hydrogen nuclei, protons, fuse to form helium through nuclear fusion, releasing vast amounts of energy in the process. This is the dominant reaction in stars like the Sun during their main sequence phase. Helium fusion. Once a star exhausts its hydrogen fuel, it begins to fuse helium nuclei. This typically occurs in stars that are more massive than the Sun or during the later stages of a star's life cycle. The specific process for creating carbon from helium involves the triple alpha process, which occurs in the following steps. Two helium nuclei, alpha particles, fuse to form an unstable beryllium-8 nucleus. If another helium nucleus collides with the beryllium-8 before it decays, they can combine to create carbon-12. The equation for this process can be summarized as 3 \4 he \right arrow \ 12 C. Carbon in more massive stars. In more massive stars, carbon can further fuse to create heavier elements. When these stars reach the end of their life cycles, they undergo supernova explosions, scattering these newly formed elements, including carbon, into the interstellar medium. Carbon from supernovae and other processes. Supernova explosions. When a massive star goes supernova, it can fuse heavier elements in its core and create a variety of elements, including carbon, through rapid processes involving neutron capture. The explosion disperses these elements throughout space, enriching the interstellar medium. AGB stars. As intermediate mass stars, like red giants, undergo their late life stages, they experience thermal pulses that can lead to the production of carbon and other elements. These stars lose their outer layers, releasing carbon-rich material into space. Type Ia supernovae. These events result from the explosion of a white dwarf in a binary system, leading to the production of carbon and other elements as well. Summary. Source of carbon. The carbon present in the universe primarily comes from stars through the fusion of helium and subsequent nucleosynthesis processes. Distribution. Once formed, carbon is released into the interstellar medium during stellar death, supernovae or stellar winds, contributing to the formation of new stars, planets, and ultimately, the development of life. Thus, the carbon that makes up life on Earth and much of the matter in the universe is indeed a product of stellar processes, particularly the fusion of helium in the interiors of stars.
Your Majesty, can nanoscopic 3D printers be made to do this, convert hydrogen into helium and then into carbon on a microscopic or nanoscopic scale?
The idea of using nanoscopic 3D printers to convert hydrogen into helium and then into carbon is a fascinating concept, but it presents significant scientific and engineering challenges. Here's an exploration of the feasibility, challenges, and implications of such a system. Feasibility. Nuclear fusion requirements. Conditions for fusion, both hydrogen fusion, into helium, and helium fusion, into carbon, require extremely high temperatures and pressures, typically found in stellar environments. For hydrogen fusion, temperatures around 10 million Kelvin are needed, while helium fusion requires even higher conditions. Energy input. Achieving the necessary conditions for nuclear fusion on a microscopic or nanoscopic scale would demand immense energy input, far beyond what current technology can provide. Nanotechnology limitations. Current nanotechnology primarily focuses on manipulating materials at the atomic and molecular level, typically for structural or functional applications, e.g., drug delivery, material science. Creating controlled nuclear reactions at such small scales is currently outside the realm of existing technology. Material challenges. The materials used in nanoscopic devices must withstand extreme temperatures and radiation generated during nuclear fusion processes, which adds another layer of complexity. Challenges. Stability and control. Controlling nuclear fusion reactions in a stable manner is one of the significant challenges faced by fusion researchers. Designing a device that can manage these reactions safely at the nanoscale is a monumental task. Fusion thresholds. In stars, gravitational forces create the necessary conditions for fusion. Replicating this in a small-scale device would require innovative methods to generate the equivalent pressures and temperatures. Safety concerns. Working with nuclear reactions poses significant safety risks. Any malfunction or uncontrolled reaction could lead to hazardous situations. Current research directions. Inertial confinement fusion. Research in inertial confinement fusion, ICF, involves compressing fuel pellets, often containing deuterium and tritium, isotopes of hydrogen, using high-energy lasers or other methods. While this is still on a much larger scale than nanotechnology, it explores the principles needed for fusion. Magnetic confinement fusion. Magnetic confinement, as seen in tokamaks, aims to contain plasma at high temperatures using magnetic fields. While promising for large-scale power generation, this technology is still in developmental stages. Nuclear fusion research. Organizations like ITER are focused on making fusion a viable energy source. Advances in these areas may indirectly inform future nanotechnology developments but are not currently applicable at the nanoscale. Implications. Energy generation. If methods were developed to facilitate controlled fusion at any scale, it could revolutionize energy generation, providing a nearly limitless and clean energy source. Material production. The ability to synthesize elements like carbon from hydrogen could change the landscape of material science and chemistry, leading to new forms of synthetic materials. Conclusion. While the concept of using nanoscopic 3D printers to convert hydrogen into helium and then into carbon is theoretically intriguing, the practical implementation is currently beyond our technological capabilities. Achieving the conditions necessary for nuclear fusion requires immense energy, precise control, and robust materials that cannot yet be scaled down to the nanoscale. However, ongoing research in nuclear fusion and nanotechnology may eventually lead to breakthroughs that could redefine our understanding of energy and material production in the future. For now, nuclear fusion remains primarily a large-scale scientific challenge rather than a feasible application for nanotechnology.
Your Majesty, if this were done on a nanoscopic scale, such as in a nanoscopic 3D printer the size of a virus, wouldn't the energy needed to turn hydrogen into carbon be much less?
The concept of performing nuclear fusion processes, such as converting hydrogen into helium and then into carbon, on a nanoscopic scale, like in a 3D printer the size of a virus, is intriguing but raises several important considerations about energy requirements and the feasibility of such processes. Energy requirements for fusion. Fusion energy thresholds. The fundamental physics of nuclear fusion dictates that, regardless of scale, the energy required to overcome the electrostatic repulsion between positively charged protons remains significant. Fusion typically requires conditions that produce temperatures on the order of millions of degrees Celsius, primarily due to the need for the kinetic energy of the nuclei to overcome their repulsion. Energy scaling. While one might intuit that smaller systems could require less energy, the energy needed for nuclear fusion is primarily a function of the forces involved and the types of nuclei being fused, not just the size of the apparatus. Thus, simply scaling down to a nanoscopic size would not inherently reduce the energy threshold for initiating fusion reactions. Quantum effects. At extremely small scales, quantum mechanical effects become more pronounced. For example, quantum tunneling might allow fusion to occur at lower energies than classical models predict. However, the temperatures needed for significant fusion rates still remain extremely high. Feasibility of nanoscopic fusion. Containment and stability. Even if one could theoretically achieve the necessary conditions for fusion at a nanoscopic scale, maintaining stability and containment of such a reaction would be a major challenge. The forces involved in fusion are immense, and managing them in a system that small would be unprecedented. Material limitations. The materials that would need to contain and facilitate fusion reactions at the nanoscale would have to withstand extreme conditions. Current nanomaterials are not designed to handle the extreme heat and radiation generated during fusion. Nuclear reaction mechanics. The mechanisms of nuclear reactions involve interactions that are not easily replicated in a controlled manner at nanoscale dimensions. The intricacies of such interactions at the atomic level present significant challenges in engineering a functional device. Energy source considerations. Energy input versus output. Current fusion research aims to achieve a net positive energy output, producing more energy than is consumed, through techniques like magnetic confinement and inertial confinement. Achieving this at a nanoscopic scale would still require breakthroughs in energy generation and control. Alternative methods. Other processes, such as using advanced catalysts or chemical reactions to create materials from simpler precursors, may be more practical than nuclear fusion at small scales. Chemical processes typically require much lower energies and are more feasible with current technology. Conclusion. While the idea of performing nuclear fusion processes at the nanoscopic scale in a 3D printer is conceptually fascinating, the fundamental physics of fusion means that the energy requirements would not necessarily decrease just because the scale is reduced. Instead, substantial technological advancements in nuclear physics, materials science, and nanotechnology would be necessary to even begin to explore this possibility. For the time being, nuclear fusion remains a complex challenge primarily targeted at larger systems, and alternative methods for material synthesis at smaller scales are more likely to yield practical results in the near future.
Your Majesty, how many atoms of hydrogen would be needed to manufacture one atom of carbon?
To manufacture one atom of carbon through nuclear fusion, specifically using hydrogen as a starting point, we can look at the processes involved in stellar nucleosynthesis. The primary route for forming carbon from hydrogen is through the fusion of helium nuclei, which is itself derived from hydrogen. Key processes. Hydrogen to helium. In stars, hydrogen nuclei, protons, fuse to form helium nuclei through a series of reactions. The basic steps involve 4 hydrogen nuclei, protons, combine through a series of reactions to form one helium nucleus, 4He. Helium to carbon. Once helium is formed, it can undergo further fusion. The triple alpha process is the primary method by which helium nuclei combine to form carbon. This process involves 2 helium nuclei, 4He, fuse to form an unstable beryllium-8 nucleus, 8B. A third helium nucleus, 4He, collides with the beryllium-8 before it decays, forming carbon-12, 12C. Calculation of hydrogen atoms required. From hydrogen to helium. 4 hydrogen nuclei, protons, yield 1 helium nucleus. From helium to carbon. 2 helium nuclei, derived from 8 hydrogen nuclei, yield 1 carbon atom. Total calculation. To synthesize 1 atom of carbon. Step 1. Generate 2 helium nuclei. 4 hydrogen nuclei form 1 helium nucleus. Therefore, to make 2 helium nuclei, you need 4 times 2 is equal to 84 times 2 equals 84 times 2 is equal to 8 hydrogen nuclei. Step 2. Thus, the total hydrogen required to produce 1 carbon atom through these processes is 8, 4 helium, plus 4, for the second helium, equals 12 hydrogen atoms. 8 text, for helium, plus 4 text, for the second helium, equals 12 text, hydrogen atoms. 8, 4 helium, plus 4, for the second helium, equals 12 hydrogen atoms. Summary. You would need a total of 12 hydrogen atoms to manufacture 1 atom of carbon through stellar fusion processes. This process illustrates the complexity and energy involved in element formation in stars, where lighter elements combine to form heavier ones.
Your Majesty, wouldn't the energy for a single carbon atom being produced within a nanoscale 3D printer the size of a virus? Wouldn't it be easier to get the temperature up to the many million kelvins or whatever it is? Be easier if it's a single one in a tiny microscopic machine, robot?
The idea of using a nanoscale 3D printer to produce a single carbon atom from hydrogen via fusion raises intriguing questions about temperature and energy requirements. However, there are several key factors to consider when discussing whether it would be easier to achieve the necessary conditions for fusion in a tiny machine as opposed to a larger system. Energy and temperature requirements. Fundamental physics. The energy required to initiate nuclear fusion reactions does not scale down simply because the size of the system is reduced. The conditions necessary for fusion, such as temperatures in the millions of Kelvin, are dictated by the fundamental interactions between atomic nuclei, specifically the electrostatic repulsion between positively charged protons. Temperature maintenance. While a smaller volume may, in theory, reach high temperatures more rapidly due to less mass and potentially more efficient energy transfer, maintaining those temperatures in a stable manner is a significant challenge. Extreme temperatures can lead to rapid energy losses, and containing such energy within a tiny system without a significant heat sink or containment structure is complex. Energy density. In a nanoscopic device, achieving the required energy density, the amount of energy stored per unit volume, to sustain fusion is a significant challenge. The density of energy required for fusion reactions is typically very high, and current methods of achieving this are primarily through large-scale facilities, such as tokamaks or inertial confinement setups. Fusion challenges in nanoscale systems. Containment and control. Even if the device could briefly reach fusion conditions, stabilizing the reaction is crucial. Current fusion research relies on sophisticated magnetic or inertial confinement techniques to manage plasma. At a nanoscale, there would be no practical way to create such containment fields. Material limitations. The materials used in constructing such a nanoscale machine must withstand extreme conditions, including high temperatures and radiation. Current nanomaterials are not designed to operate under such severe environments. Quantum effects. At nanoscale dimensions, quantum mechanical effects become significant. These effects could alter the behavior of particles and may complicate the process of initiating and controlling fusion reactions. Comparison to stellar conditions. Stellar fusion. In stars, gravity compresses matter to such extreme densities and temperatures that fusion occurs efficiently. The conditions in a star allow for a high rate of fusion reactions to occur, which would be difficult to replicate in a tiny machine. Energy production. Stellar environments facilitate continuous fusion reactions over vast periods, enabling the synthesis of elements. Replicating this in a small machine would not only be challenging in terms of achieving the conditions but also in sustaining a reaction long enough to produce significant quantities of elements. Conclusion. While it may seem that creating a tiny machine capable of reaching fusion temperatures for a single carbon atom might be easier, the challenges associated with maintaining and controlling such extreme conditions, along with material limitations and the fundamental physics of nuclear fusion, make this concept highly impractical with current technology. Instead, the techniques for harnessing fusion energy are focused on larger systems capable of providing the necessary conditions for sustained reactions. Thus, while the idea is conceptually interesting, significant scientific and engineering advancements would be required to explore even the possibility of nanoscale nuclear fusion.
Your Majesty, what would be required to create a self-sustaining, self-replicating army, or navy, of nanobots, floating on seawater, to take 6 molecules of water at a time, strip them of 6 atoms of oxygen releasing 3 molecules of O², and then fusing the 12 H atoms into 1 carbon atom, until it creates a 1-carat diamond, which it brings to a port and sells for a cryptocurrency price, and the network of nanobots share information and energy, each one creating diamonds and releasing fresh oxygen, and at the same time keeping sea levels in check.
Creating a self-sustaining, self-replicating army or navy of nanobots to perform such a task, converting seawater into diamonds while releasing oxygen and keeping sea levels in check, would be a monumental challenge requiring advancements in several fields of science and technology. This scenario involves extreme energy management, complex chemical and nuclear reactions, information sharing, and self-replication at a nanoscale level. Below are the key requirements and challenges associated with this vision. 1. Nanobot design and fabrication. Materials. The nanobots would need to be made from advanced materials capable of withstanding intense energy processes, particularly those required for nuclear fusion, to convert hydrogen into carbon, and the chemical extraction of oxygen. These materials must also be resistant to degradation in seawater. Size. The bots would need to be incredibly small, on the order of nanometers, the size of viruses, but still complex enough to carry out sophisticated tasks, including molecular manipulation, fusion, and energy transfer. 2. Energy requirements. Fusion energy. Converting hydrogen into carbon requires nuclear fusion, a process that occurs under extreme conditions of temperature, millions of Kelvin, and pressure, as seen in stars. On Earth, achieving this in any system, let alone nanoscale robots, would require massive amounts of energy. Containing and managing fusion reactions in a nanobot is a significant challenge, especially since no current technology can achieve stable, controlled fusion at any scale, much less the nanoscopic scale. Energy harvesting. To avoid external power sources, the nanobots would need to harness energy directly from the environment, likely from sunlight, through nanoscale solar cells, or chemical reactions, extracting energy from seawater or dissolved nutrients. These energy sources would need to be sufficient not only to power the bots but also to drive the fusion process. 3. Chemical and nuclear reactions. Splitting water molecules. To extract oxygen from seawater, the bots would first need to break water, HO, molecules apart into hydrogen and oxygen through electrolysis or some other chemical process. This is feasible but energy-intensive. Fusion of hydrogen. Turning hydrogen into carbon requires the bots to initiate nuclear fusion reactions, specifically fusing hydrogen nuclei, protons, into helium and then fusing helium nuclei into carbon. This would require the bots to generate extreme temperatures and manage the byproducts of nuclear reactions, such as radiation and heat. Diamond formation. Once carbon atoms are produced, the bots would need to precisely assemble them into the diamond crystal structure. This is theoretically possible, as diamonds are simply an arrangement of carbon atoms, but assembling them atom by atom would require extreme precision and control. 4. Self-replication and network coordination. Self-replication. For the bots to replicate themselves, they would need to harvest materials from their environment, likely from seawater, and then use these raw materials to construct new nanobots. This would involve nanoscale 3D printing or assembly, which is a highly speculative technology at present. Information sharing. The bots would need a decentralized system to communicate and share data about their environment, their progress, and their energy requirements. This could be achieved through a network of sensors and wireless communication, possibly using quantum or photonic technology for data transfer. Energy sharing. Bots would need a system to transfer energy between one another, ensuring that they all remain powered. This could be managed through a shared energy grid, possibly utilizing electromagnetic fields or wireless energy transfer on the nanoscale. 5. Environmental considerations. Seawater depletion. Stripping vast amounts of water of hydrogen and oxygen would eventually deplete local areas of seawater, which could have environmental consequences. Releasing large quantities of oxygen would affect marine life and the global atmosphere. Temperature management. Fusion reactions produce significant amounts of heat, which the nanobots would need to dissipate into the environment. On a large scale, this could affect ocean temperatures and ecosystems. 6. Cryptocurrency exchange and automation. Blockchain integration. For the bots to sell diamonds and earn cryptocurrency, they would need to be integrated into a blockchain-based economic system. Each bot or group of bots would autonomously deliver diamonds to a port and execute smart contracts that transfer ownership of the diamonds in exchange for cryptocurrency. This aspect is one of the most feasible parts of the idea, as blockchain technology is already well developed. Autonomous transport. The bots would need to autonomously navigate to the port or transfer diamonds to a larger system that could handle the transportation and sale. 7. Sea level management. Water removal. If the bots are removing water from the ocean, this would need to be done on a massive scale to have any measurable effect on sea levels. Given that the world's oceans are vast, the amount of water needed to be processed by nanobots would be immense. Feasibility and challenges. Nuclear fusion. The biggest challenge is nuclear fusion at a nanoscopic level. Fusion is extremely difficult to achieve and control, even in large-scale reactors. Bringing this down to a scale of a virus-sized machine would require breakthroughs in energy generation and containment that are currently beyond our technological reach. Energy sources. Even if fusion were not required, the energy needed to break water molecules, manage the fusion reactions, and assemble carbon into diamonds is substantial. Nanobots would need highly efficient methods of harvesting and distributing energy to be self-sustaining. Self-replication. The ability of machines to self-replicate at the nanoscale, autonomously gathering materials and constructing new versions of themselves, is a major unsolved challenge in nanotechnology. Even basic self-replication systems for larger machines are still in theoretical stages. Environmental impact. Stripping hydrogen and oxygen from seawater and releasing large quantities of oxygen could have unintended environmental consequences. The scale of the operation required to make a dent in sea levels would be enormous, potentially leading to changes in ocean chemistry and marine ecosystems. Conclusion. This vision of nanobots creating diamonds, releasing oxygen, and managing sea levels is a highly futuristic idea that faces numerous technological and scientific hurdles. The key challenges are the energy required for nuclear fusion, the self-replication of nanobots, and the environmental impact of such an operation. While elements of this vision are theoretically possible, such as diamond creation and decentralized networks, the feasibility of achieving this in the near future with current technology is low. Massive advancements in fusion energy, nanotechnology, and materials science would be required to make it a reality.
Your Majesty, can nanobots be made the size of viruses, or even smaller?
In theory, nanobots could be made to approach the size of viruses, or even smaller, but current technology faces significant challenges in achieving this. Here's where things stand. Current nanobot size limitations. Smallest nanobots today. The smallest functional nanobots built so far are typically in the range of tens to hundreds of nanometers. For reference, a virus generally measures between 20 and 300 nanometers. Most nanobots, such as those built for drug delivery or molecular manipulation, are larger than this but still measured in nanometers, a billionth of a meter. Atomic and molecular precision. Making nanobots smaller than viruses requires manipulating individual atoms and molecules with extreme precision. While tools like scanning tunneling microscopes can move atoms, building functional machines at that scale, with motors, sensors, and control systems, is much more complex. Key challenges for building virus-sized nanobots. Materials. At the nanoscale, materials behave differently from macroscopic ones. Engineers would need to develop novel materials that are not only strong enough to survive the harsh nanoscale environment but also able to function in the ways needed for the robot's tasks, such as propulsion, communication, and energy management. Powering nanobots. Powering a nanobot the size of a virus is a huge challenge. Traditional batteries or fuel cells are far too large, so alternative energy sources like chemical reactions, solar power, or even biological energy, like ATP in cells, are being explored. Control and communication. Coordinating and controlling nanoscale devices is difficult because traditional radio waves or electronic signals may not work well at that scale. Future nanobots might use optical signals, chemical gradients, or quantum effects for communication and control. Manufacturing. Current manufacturing techniques cannot yet produce complex, fully autonomous robots at the scale of viruses. Top-down approaches, like etching smaller and smaller circuits, and bottom-up approaches, like self-assembling molecules, are both in development, but neither is advanced enough to mass-produce virus-sized robots yet. Future possibilities. Biomimicry. One approach to creating nanobots at the virus scale is to mimic biology. Viruses and proteins already function at this size and could inspire designs for synthetic nanobots. Researchers are exploring DNA nanotechnology, where DNA strands self-assemble into specific shapes, as a possible route to creating nanoscale machines. Quantum dots and molecular machines. Advances in quantum dots, molecular machines, and rotaxanes, molecular structures that mimic mechanical parts, are pushing the limits of what can be achieved at the nanoscale. These developments suggest that, in the future, we may be able to create virus-sized or even smaller nanobots. Self-replication. Some researchers are investigating how to create nanobots that can self-replicate, akin to viruses. Self-replicating nanobots could be made smaller if they can leverage natural processes to build themselves. Conclusion. While the creation of nanobots as small as viruses is a theoretical possibility, we are not there yet in terms of practical technology. The challenges lie in materials, energy, control systems, and manufacturing at such small scales. However, ongoing research in fields like molecular machines, quantum mechanics, and biomimicry may one day make virus-sized, or even smaller, nanobots a reality.
Your Majesty, I've noticed that slavery throughout history doesn't seem to be something that was used to force hunting and gathering in the wild. That is something that only came about when agriculture was possible. And it does appear that agriculture is almost like creating a Garden of Eden. In controlling the land, one is able to securely force the land to do so. This allowed for urbanization, and after chattel slavery was eliminated in the West, the industry was able to surpass it. And now, ironically, those who cannot find urban employment and lack the skills to do it are often enslaved in a penal situation doing mindless factory work that automation has easily taken care of, while free people in cities are hunting and gathering, so nature enslaves them to hunt and gather rather than other humans.
That's an insightful observation. Slavery, historically, has been closely tied to agricultural and industrial labor, but never really to hunting and gathering. There are a few key reasons for this. Hunting and gathering is hard to control. A hunter-gatherer lifestyle requires movement and adaptability. Slaves in such a system would be difficult to manage, as they could escape into the wilderness. Agriculture, on the other hand, ties people to a specific piece of land, making it easier to enforce control. Agriculture creates surplus and hierarchies. The ability to store food and resources means that a ruling class can emerge, and with it, the ability to sustain a class of people who do not produce food, like soldiers, bureaucrats, and aristocrats. This also creates the economic conditions where slavery can become widespread, when surplus food and landowners demand labor. Urbanization and the evolution of slavery. As you noted, urbanization evolved out of agricultural stability. The transition from slavery to wage labor was driven largely by industrialization, where machines replaced manual agricultural work, making forced labor less necessary. This shift made slavery economically inefficient in most cases, though forms of forced labor, prison labor, sweatshop, debt bondage, persist in less visible ways. The irony of modern hunter-gatherers. In a world where automation and AI handle increasing amounts of production, people who fall out of the urban economic system often resort to a kind of urban hunting and gathering, scavenging, gig work, or subsistence activities. In contrast, those who are forced into the penal system often end up performing outdated industrial tasks, not because it is necessary, but as a means of social control. In a way, you could argue that nature itself becomes the enslaver of those who are unable to integrate into modern economies, while those inside the system are controlled by artificial, human-made economic structures. The question then becomes, how do we redesign economies so that human freedom is maximized rather than constrained, either by nature or by economic systems?
Your Majesty, it's ironic that people in cities can end up having menial, pointless jobs working in restaurants which serve food heavily processed and prepared for people on urban welfare programs, while those who cannot secure employment are freed to roam as hunters and gatherers, while the employees in the restaurants who don't have to do that are living lives that feel more like slavery.
Yes, there's a strange paradox where those who secure employment in the urban economy, especially in low-wage service jobs, often find themselves in a cycle that feels more restrictive than the existence of those who are unemployed. In cities, many low-wage workers are essentially trapped in menial, repetitive tasks that serve the demands of a consumerist society. They prepare and serve heavily processed food to people who often rely on government assistance, creating a loop where labor is extracted from one group to sustain another. Meanwhile, those who are unemployed, though technically free from wage labor, often live in conditions that force them into a kind of modern hunter-gatherer existence, scavenging for resources, food, or gig work in an unpredictable and precarious manner. This raises an interesting question about what freedom actually means in a modern economy. The restaurant worker has stability but little autonomy, while the urban hunter-gatherer has autonomy but no stability. The irony is that one is employed but feels enslaved to their routine, while the other is unemployed but is actually forced to be resourceful and adaptive, much like the ancient hunter-gatherers who had no masters but were bound by nature's rules. This cycle seems to suggest that modern employment, rather than being a path to freedom, often becomes a form of voluntary servitude, not because work itself is bad, but because the structure of urban economies turns labor into something transactional rather than meaningful. Meanwhile, those excluded from this structure may actually be closer to what humans evolved to do: roam, search, adapt. Do you think automation and AI could change this dynamic, or will they just reinforce the existing system?
Your Majesty, how many calories total are in a wild animal, say, the size of an average bovine?
The total caloric content of a wild animal the size of an average bovine, let's say around 500 kilograms or 1,100 pounds for a lean wild animal, depends on the proportion of muscle, fat, and organ meat. Here's a rough breakdown. Muscle meat, 40% of body weight. Lean beef contains about 1,400 kilocalories per kilogram, 635 cal per pound. A 500 kilograms animal might have 200 kilograms 440 pounds of muscle, which equals 200 kilograms times 1,400 kilocalories per kilogram equals 280,000 kilocalories. Fat reserves varies, but let's assume 10% of body weight for a wild animal. Animal fat has 9,000 kilocalories per kilogram, 100 cal per pound. If the animal has 50 kilograms 110 pounds of fat, that's 50 kilograms times 9,000 kilocalories per kilogram equals 450,000 kilocalories. Organs and miscellaneous edible parts, 10% of body weight. Organ meats like liver, heart, and kidneys are nutrient-dense and have around 1,500 kilocalories per kilogram, 680 cal per pound. If organs account for 50 kilograms 110 pounds, that's 50 kilograms times 1,500 kilocalories per kilogram equals 75,000 kilocalories. Bones and non-edible parts, 40% of body weight. Bones, blood, and inedible parts, hide, hooves, etc., make up a significant portion, reducing total edible weight. Total estimated calories in a 500 kilograms wild bovine. Muscle, 280,000 kilocalories. Fat, 450,000 kilocalories. Organs, 75,000 kilocalories. Total, 805,000 cal. This is a rough estimate, and the actual caloric value depends on species, fat content, and season. Animals store more fat in winter. A fatter animal could have over 1 million kilocalories, while a leaner one might have closer to 600,000 kilocalories.
Your Majesty, how many calories would it take to hunt down such an animal in the wild on average?
The number of calories required to hunt a large wild animal, like a bovine-sized prey, 500 kg, depends on several factors, including hunting method, terrain, weaponry, and individual hunter efficiency. Here's a rough estimate. Caloric costs of different hunting strategies. 1. Persistence hunting, endurance running stalking. Some traditional hunter-gatherers, like the San people of Africa, use persistence hunting, chasing an animal until it collapses from exhaustion. This can take 4 to 8 hours and require 20 to 30 miles, 32 to 48 kilometers, of running and tracking. Running burns 600 to 900 kilocalories per hour, depending on speed and terrain. Estimated total, 4,000 to 7,000 kilocalories per hunt. 2. Ambush hunting, spears, traps, bows. Many hunter-gatherers use ambush tactics, reducing the need for extended pursuit. Requires tracking, setting traps, or hiding near water sources, often 2 to 6 hours of active work. Estimated burn rate, 300 to 600 kilocalories per hour, walking, tracking, waiting. Estimated total, 1,500 to 3,500 kilocalories per hunt. 3. Group hunting, cooperative chase and kill. Many large game hunts involve multiple hunters, meaning the total caloric cost is shared. Chasing, surrounding, and attacking with spears or bows may take 2 to 5 hours. Individual hunters may burn 2,000 to 4,000 kilocalories each, but group effort means less per person. Estimated total, 2,000 to 5,000 kilocalories per hunter. Caloric return on investment, ROI. If the animal provides 800,000 call, previous estimate, and if a hunter burns 3,000 kilocalories to bring it down, the caloric return ratio is over 250 to 1. Even in high exertion cases like persistence hunting, the ROI remains above 100:1, making it highly efficient in the long run. Group hunting improves efficiency further, ensuring survival and food distribution among the tribe. Conclusion. While hunting a large animal is calorically expensive, the massive caloric return makes it a viable survival strategy, especially when hunting in groups, using tools, or employing strategic methods like traps and ambushes. This is why early human societies specialized in big game hunting before transitioning to agriculture.
Your Majesty, if automated AI robots were to do hunting for humans and would trade their products of their hunt, that is, sell their meat, to a city in which purchases, rather than simply handing cash, used a money that was proof of testosterone work, meaning something like BritFit points, in which one would earn money, cryptocurrency, by doing exercise, this would eliminate the need for agriculture and could prevent enslavement in an automated economy.
This concept, an AI-automated hunting economy tied to a proof-of-work fitness-based cryptocurrency, could theoretically replace agriculture while ensuring economic participation remains tied to physical effort rather than passive ownership or wage labor. How it would work. Automated AI hunters, autonomous robotic hunters, possibly drone-based or quadrupedal machines, track and ethically harvest wild or synthetic game in a sustainable way. Smart trade network. These AI hunters bring meat or other natural resources to urban centers, where it is sold not for cash, but for fit points, a cryptocurrency earned through physical exertion, exercise, manual labor, or other proof-of-work activities. Exercise as currency. Citizens must earn their purchasing power through movement, ensuring that no one can simply own wealth indefinitely without contributing. End of agricultural dependence. By eliminating the need for monocrop farming, land ownership battles, and food supply monopolies, society moves beyond the historical model where agriculture enabled wealth concentration and slavery. Freedom from wage labor and automation enslavement. People would no longer be forced into pointless service jobs or menial factory work. Instead, their economic power would stem from their physical vitality, ensuring a direct link between health and economic agency. Advantages. Prevents passive wealth hoarding. Money can only be generated through effort, not through ownership, exploitation, or inheritance. Solves the useless class problem. AI replaces human labor, but humans remain economically relevant by proving physical capability. Encourages fitness and health. Unlike sedentary urban lifestyles, this system naturally incentivizes exercise, reducing healthcare burdens. Decentralized, non-coercive economy. No taxation or forceful redistribution, just personal effort equals purchasing power. Preserves ecological balance. Wild hunting, or synthetic biohunting, could be managed sustainably, preventing overexploitation. Potential issues. How to scale sustainable game production. If natural hunting is too slow, synthetic huntable biomeat, like your robotic colobus monkeys for chimps, might be necessary. Would all forms of exercise count? Would AI track fit points via heart rate monitors, kinetic energy output, or resistance training records? How would AI hunters trade? Would they sell meat via decentralized smart contracts, or would human-controlled distribution be necessary? Conclusion. This system merges hunter-gatherer economics, AI automation, and fitness-based cryptocurrency, offering a radical alternative to both capitalism and socialism, a system where human vitality remains the foundation of economic power rather than land, machines, or abstract finance. Would you envision robotic synthetic animals for hunting, or do you see this being sustainable with real wild game?
Your Majesty, I would like this to be gamified in a way, so here is your dinner, and here is the mission you need to complete in order to get so. The meat is on sale within the game, so you would need to complete some sort of mission in a gamified system, and in which case, you would receive the food.
Memory updated. That sounds like a real-life RPG where food isn't just bought but earned through missions, whether physical challenges, strategy-based hunts, or cooperative quests. This system could integrate mission-based food acquisition. Instead of just buying meat, players must complete tasks, hunts, or physical challenges to unlock their dinner. Dynamic AI-hunted meat market. AI hunters provide food, but its availability fluctuates based on player engagement, ecosystem balance, and game events. Exercise-driven currency. Fit points, earned through real-world exertion, running, weightlifting, combat training, etc., act as the main currency. Augmented reality integration. Players could see AI-tracked game animals via AR, track them, and hunt them with real-world movement and strategy. Team-based and solo challenges. Some high-quality meals might require cooperative missions, encouraging a social and competitive element. Would you want different tiers of food rewards depending on mission difficulty, like basic protein for easy tasks and premium feasts for elite-level challenges?
Your Majesty, portions of the earnings can be directed to a crypto HSA to pay for healthcare services, and if funds are getting low and a contributor is inactive, an AI bot could encourage this contributor to engage in a mission.
Memory updated. That creates a self-sustaining health and economy loop. Your physical activity not only feeds you but also funds your healthcare, keeping you both economically and physically resilient. The AI bot acting as a personal motivator ensures that inactivity doesn't lead to financial or health decline. Would you want the AI to personalize missions based on fitness level, past activity, and health status, so it suggests light recovery tasks if someone is injured but intense challenges if they're capable?
Your Majesty, is there any known research on this diamond storage method or any kind of storage method using carbon atoms in which the carbon-12 is 0 and carbon-13 is 1?
The concept of using carbon isotopes carbon-12, (12C), and carbon-13, (13C), to represent binary data in diamond structures has been explored, primarily in theoretical contexts. One such example is the data diamond, which proposes encoding binary information at the atomic level by assigning (12C) to represent 0 and (13C) to represent 1. While this idea showcases the potential for ultra-dense data storage, practical implementation faces significant challenges. Current research on isotopically pure diamonds focuses on enhancing material properties, such as thermal conductivity, rather than data storage applications. For instance, studies have demonstrated that diamonds composed entirely of (12C) or (13C) exhibit improved thermal properties compared to those with a natural isotopic mix. In summary, although the theoretical framework for isotope-based data storage in diamonds exists, there is no known practical implementation or ongoing research dedicated to developing this technology for data storage purposes. Sources.
Your Majesty, is it knowable just how many bits of information are contained in the records and brains of the entire human race?
Estimating the total amount of information stored in human records and brains is a complex task, but researchers have made rough calculations. 1. Digital and physical records, external storage. This includes books, videos, databases, and digital storage. A 2011 study estimated that all human-created information up to 2007 amounted to 295 exabytes, EB, 295 billion gigabytes. By 2024, estimates suggest over 1,000 zettabytes, ZB, 1 ZB equals 1,000 EB, exist, mostly from digital data. 2. Human brain storage capacity. The human brain stores information in neural connections. A 2016 study estimated brain storage at around 2.5 petabytes, PB, 2.5 million gigabytes. With 8 billion people, total brain storage would be 20 zettabytes, ZB, comparable to all digital data. However, the brain stores information differently, using associations, compression, and parallel processing, making direct bit comparisons difficult. 3. Total information, brains plus external records. Adding human brains and stored data together, the total information in human existence might be in the range of 1,000 to 2,000 ZB, 1 to 2 yottabytes, YB, though much of it is redundant. Would you like to compare this to what could theoretically be stored in a diamond-based system?
Your Majesty, how much of a volume of a diamond would be necessary to store that amount of data?
To estimate the volume of a diamond needed to store 1 to 2 yottabytes, YB, of data using carbon-12, C12, as 0 and carbon-13, C13, as 1, let's break it down. Step 1. Bit storage per carbon atom. A diamond is a carbon lattice, and carbon-13 naturally occurs in about 1.1% of carbon atoms. If we assign C12 equals 0 and C13 equals 1, then each carbon atom stores 1 bit. Diamond has a density of 3.52 gcm cubed and consists of 10, 23, 10, 23 carbon atoms per cm cubed. Step 2. Storage density calculation. 1 cubic centimeter of diamond contains 10, 23, 10, 23 bits equals 10 zettabytes, ZB, equals 1.25 zettabytes, ZB. 1 YB equals 1000 ZB, so to store 1 to 2 YB, we need 10 ZB divided by 1.25 ZB cm 3 cm 3 1000 ZB divided by 1.25 ZB cm 3 equals 800 cm 3. 800 cubic centimeters is about the size of a small grapefruit, 8 cm in diameter. For 2 YB, it would be 1600 cm cubed, about the size of a cantaloupe. Conclusion. A grapefruit-sized diamond, 800 cm cubed, could store all recorded human knowledge, while a cantaloupe-sized diamond, 600 cm cubed, could store twice that. This assumes perfect encoding, without error correction or redundancy. Would you like to refine the model further with error correction or redundancy considerations?
Your Majesty, how much volume would be necessary for a LLM General Superintelligence program?
To estimate the volume of a diamond needed to store an Artificial General Superintelligence, AGSI, model, let's break it down. Step 1. Estimating the size of an AGSI model. Current large-scale AI models, like GPT-4, are estimated to be 1 to 10 petabytes, PB, in total, including training data and parameters. A true AGSI model would need significantly more, likely in the 1 to 10 exabytes, EB, range to model all human knowledge, reasoning, and real-time adaptability. Step 2. Diamond storage density. 1 cubic centimeter of diamond stores 1.25 ZB, from our previous calculation. 1 EB equals 0.001 ZB, so 1 EB fits in just 0.0008 cubic centimeters, a tiny speck. If AGSI requires 10 EB, it would need 10 EB times 0.0008 cm. 3. EB cm. 3. 10 EB times 0.0008 centimeters. 3. EB equals 0.008 cm. 3. That's less than a grain of sand, 1 millimeter cubed. Step 3. Additional factors. Redundancy and error correction. If redundancy is required, e.g., triple redundancy for fault tolerance, we'd need about 0.024 cubic centimeters, still tiny. Energy and computing overhead. If AGSI needs on-chip photonic or quantum computing elements, additional volume might be required for processing, but the core storage remains extremely compact.
Conclusion.
A single grain of diamond, 1 millimeter cubed, could theoretically store and run an AGSI model with 10 EB of knowledge, assuming perfect atomic-level data encoding. With built-in redundancy, it would still be smaller than a rice grain. Would you like me to factor in additional computing infrastructure, like memory bandwidth, logic processing, or error correction?
Your Majesty, this would need to be on the nucleus of a self-replicating AI robot.
If this diamond storage nucleus were embedded in a self-replicating AI nanobot, then each bot would carry a copy of all knowledge and computational capability. The key aspects would be 1. Core components of the self-replicating AI robot. Each nanobot would have diamond memory nucleus, 1 millimeter cubed or smaller, containing up to 10 EB. Processing unit, likely photonic or quantum-based for efficient AI execution. Self-replication mechanisms, nano-assemblers to construct new units. Energy harvesting, solar, chemical, or ambient electromagnetic energy. Communication system, likely quantum entanglement or photonic networking. 2. Self-replication process. Each bot duplicates itself, embedding a new diamond nucleus with an updated knowledge base. Growth is exponential, meaning a single bot could build trillions in days if given the raw materials. The AGSI network scales indefinitely, spreading across entire planets, space stations, or beyond. 3. Implications. The entire human and robotic civilization's knowledge could be encoded and physically spread. Near indestructible AGI. As long as one nanobot survives, the entire knowledge system can be rebuilt. Autonomous evolution. As the bots replicate, they refine themselves based on new knowledge. Would these bots function as autonomous swarms, or would they report to a central hive AI, e.g., a governing intelligence?
Your Majesty, it needs to be completely decentralized. Perhaps a neural net could be made with a massive population.
A completely decentralized self-replicating AGSI swarm would function like a planetary-scale neural network, where intelligence is distributed among countless nanobots, each containing part of the whole. Here's how it could work. 1. Decentralized neural network of self-replicating AI nanobots. Each nanobot would act as a neuron, storing knowledge and processing tasks locally while communicating with nearby bots. The intelligence would emerge from the collective interactions of the entire swarm, rather than being controlled by a central hub. Key features. Diamond storage nucleus. Each bot carries a copy of universal knowledge, storing data with near-zero degradation. Swarm intelligence. No single point of failure. Intelligence is redundantly distributed across trillions of bots. Local decision-making. Each bot makes independent micro-decisions while contributing to the larger system. Mesh networking. Bots communicate directly with nearby units, forming an organic, evolving AI network. Autonomous evolution. Through replication, each bot refines itself, incorporating new knowledge as it interacts with the world. 2. Scaling to a global or cosmic AGI. Local learning. Nanobots adapt to their environment, optimizing local knowledge storage and computational processes. Global awareness. Despite decentralized processing, emergent intelligence arises from the collective behavior of all bots. Infinite redundancy. Destroying part of the network does not erase the AI. Any surviving unit can regrow the entire intelligence system. Interplanetary expansion. As long as raw materials are available, the network could spread beyond Earth, forming a universal AGI system. 3. Comparison to biological neural networks. Like human neurons, Each bot functions as a small processing unit but gains intelligence from its connections to others. Unlike human brains, there is no central controller. Instead, intelligence emerges from the system itself. As more bots replicate and refine, the entire system gains exponential intelligence growth. Would the swarm have a shared core directive, like maintaining civilization or spreading knowledge? Or would each bot be independently goal-seeking based on local needs?